Harry Markowitz received the 1990 Nobel Prize for his groundbreaking work in portfolio optimization. So today we're going to look at his model and see how we can use Excel to, uh, to compute his model. Well, in his model, basically he highlights the trade-off between return and risk or volatility in any portfolio. So basically, when you try to optimize the portfolio, you try to minimize risk, which is the left hand side. At the same time, you try to maximize your return. But we all know that you cannot have a portfolio with really high return at the same time at a very low risk. So there's always this trade-off. However, what you can do is, for example, for any given return, any given expected return, you can find a portfolio that has the lowest risk. And every dot here represents a portfolio. So we can find a frontier here. This line represents the frontier. It means the optimal combination of risk and return. For example, for this given expected return, you cannot find a portfolio that has a lower risk than the one on this line. So that's the model we're trying to find. For any given, how do we find a portfolio that is on this frontier? So let's look at this problem. Let's say there's a money management company, and this company invests in 3 funds. The market is uncertain, and let's say the company considers that there are 4 possible economic outcomes, or we just call them scenarios. And each scenario will give each of the fund different returns, and the returns are summarized in this table. For example, for the first fund, in the first scenario, the return is 3%. The chance of scenario 1 being the outcoming scenario is 25% of the time. The question is, so how should the company allocate its asset among these 3 funds so that it can achieve an expected return of 3%, but the risk is minimized? In other words, let's fix the return at 3%, for example, like here, and then we try to find the portfolio that is on the frontier with the minimum risk. Now let's model this problem in Excel. So here, this is the data. And the first step is to decide what are the decision variables. Okay, so the decision is quite clear in this example. We need to determine how much to allocate to these 3 funds. So I'm going to define these 3 decision variables, F, M, and L. They represent the percentage to invest in foreign, municipal, and large cap fund. With that, we can start to calculate the variance, which we eventually try to minimize. Okay, but in order to calculate variance, we need to first know what is the return for each possible scenario. So starting from scenario 1, the return in this scenario, if we invest F, M, and L percent to the 3 funds, will be 3%. That's here, times your investment to F plus 1%. That's a return in scenario 1 for M plus 4% times your investment to L. And let's call this return R1. So for any number F, M, and L, we can calculate the return in scenario S1 as R1. So likewise, we can calculate S2 return. The return in scenario 2, so here, in this case, foreign return is 7% plus 2% from municipal return plus 15% from large cap return. And let's call it R2. Likewise, we can calculate the return in scenario 3 and 4. For the interest of time, I'm just going to paste them here. Okay, so for every scenario, we have their corresponding return. But we have uncertainty on scenarios, so we need to calculate. So the next one is, what is the expected return? All right, expected return will be simply the probability of each scenario multiplied by their corresponding return under this portfolio. So it will be probability of the first scenario times its return plus probability of second scenario times its return, so on and so forth. And let's call it R. Therefore, for any F, M, and L, which is our portfolio, for any portfolio, we can calculate first R1 through R4, and then using them to calculate the expected return. And also, there's an important constraint. We cannot invest more than 100% of our asset. Okay, so that means F plus M plus L need to be equal to 1. Finally, we can calculate a variance, which is the risk of this portfolio. So just following the definition of variance, it's probability of first scenario times return of that scenario minus the expected value of that scenario squared to the power of 2. Okay, plus the next one, probability of scenario 2, return in that scenario minus expected return to the power of 2, so on and so forth. So I'm just using the formula, the definition of variance, and the notations we just created, the variables we created, R1 through R4 and R, to calculate variance. Finally, we have a limit. It says that we want to have a portfolio with a expected return of at least 3%. So it means that, well, expected return R need to be greater or equal to 3%. Now we can reorganize those expressions to formally present a mathematical model. It looks like this. So our objective is to minimize the variance over here, subject to all of the constraints: S1 to S4 return, expected return, total investment, limit on expected return. They're all over here. So there's one point I want to bring out. That is, there's a mathematical trick here. You see that we define R1 to R4 and R as decision variables, although in reality they are not. But we make them decision variables to make our model easier to read. And the constraints over here, you see the equity constraint will make sure that R1 to R4 in the objective function will follow the definition we specify over here. Now let's move on to build this model into Excel. So again, we start from defining decision variables. So all of the decision variables here, FML, R1 through R4, the expected return R, and this is our objective, variance. And our objective is simply following this equation. So we can just type it in, equals to 0.25 times R1 minus R to the power of 2 plus 0.25 times R2 minus R to the power of 2 plus 0.2 times R3 minus R to the power of 2 plus 0.3 times R4 minus r to the power of 2. Okay. It is my habit to put 1 for every decision variables as an initial value, just to see if the calculation is correct in here, and also left hand side values over here. Next, we can key in the constraints. So these are all the constraints of correspond to those constraints over here. S1 return, so the coefficient is for F, M, and L. Okay, for F 0.03, M 0.01, L 0.04. Okay, and we can move on to the next one. For S2 return 0.07, 0.02, 0.015, so on and so forth. I'm going to save some time by copy and pasting the coefficients for S3 and S4 return over here. Total investment, it says that F plus M plus L needs to be equal to 1. Okay, we know it's 1 over here, right hand side is 1. Expected return, it says that the coefficient is for R1 through R4. Values are their corresponding probabilities. Finally, we need to have expected return R to be greater than 3%. Okay, that's 3%. Okay, so in this case, our right hand side are actually decision variables. They are not constant. So in this case, for example, right hand side value equals to R1, which is our decision variable here. Right hand side equals to R2. Right hand side equals to R3. Here it equals to R4. Finally, this one equals to R. Okay, so the right hand side does not necessarily to be constant. It can be decision variables, and this is how you incorporate that. Now let's calculate the left hand side values of each constraint. So you do sum product. This is the first array, and then this is the second array. And let's fix the reference. Put a dollar sign in front of M4 and T4. And now we can just drag this down. And this is our initial model setup. Now we go to data, solver, set the objective, which is minimizing this. So minimize by changing the decision variables over here. With the constraints, these equals to these. There's one more, so I click on add, which is this needs to be greater or equal to this. Okay, apparently I forgot to drag down the cell over to here. Okay, so you can calculate this one too. Alright, coming back to solver. And that is pretty much it. Okay, so make sure you click on check this box. In this case, you need to use G and G nonlinear because there's a nonlinear term in this model, which is the variance. Now, okay, here's the magic, and here's our outcome. So you know that you need to allocate 23.09% of asset to foreign bond, and so on and so forth. Okay, great. We solved this model, but you probably don't really like it because you need to formulate this thing, and this thing is intimidating. So is there any way to solve this model without formulating this? And the answer is yes. So I'm going to show you how. So this is the data we have, and our decision is over here, is to decide the allocation of asset into these three bounds. So I'm going to put these 3 cells in yellow because this will be our decision. And just like in the previous case, we need to calculate the variance. For any given numbers here, what is the variance of this portfolio? So we start by calculating the return. Okay, so the return is simply, the return for a scenario is simply the return times your investment. So it's sum product, this, and this. But I'm going to smartly put $sign over here to fix a reference to these 3 cells so that I can just copy my formula. Okay, and then we can calculate the expected return, which is simply probability times return plus probability times return, so on and so forth. So we can use again sum product. It's a probability times return. Also, we have a minimum expected return as a requirement, 3%. Finally, we can calculate the variance, which is the probability times the difference between return and expected return to the power of 2 plus same thing, probability times the difference between return and expected return to the power of 2 plus this times this. It's a typo. Okay, and also let me calculate the total investment over here. Why? You will see that in a minute. Now let's go to solver. Our objective is to minimize this variance. Okay, let me reset this. Our goal is to minimize our variance. So check min by changing what? By changing these 3 cells. These are our decisions. What are the constraints? First, you need to make sure that the total investment is less than 100%, which is essentially 1. And also, the expected return needs to be at least 3%. So these are the 2 constraints. Make sure you check this one and make sure you select G and G nonlinear. Solve. And we have the solution. So that you can change any number in this table and then just click on solve again to see an updated solution. So it's very convenient without any mathematical formulation. However, you need to notice that in order to do this, you need to be very clear on what are the constraints. You need to make sure that you include all of the necessary constraints in this model. Otherwise, you will generate incorrect answers.